Nowadays, it has been easy to recognize handwritten characters using a smart pen and digital screen. However, screens are often expensive, has unnecessary restrictions, and does not allow recognition in immersive technologies. In this work, we introduce a system based on deep learning that can directly convert pen's motion into either letters or arbitrary English words without the need for a screen. We made our own hardware and collected over 6,000 letter sequence dataset from 3 subjects. 300 continuous word sequences are also collected as a test set for a word reconstruction pipeline. We implemented data interpolation and resampling for the data preprocessing as in our previous work.
We first conduct data augmentation to produce more samples and closer to the distribution of continuously written words. Then we design a word reconstruction pipeline that takes a word sequence, conducts segmentation, character classification, trajectory search, and finally autocorrect to produce a prediction word string. Then we have a character classifier that's an encoder-decoder, with an LSTM encoder that encodes frames into hidden states, and a fully connected decoder that decodes into a class prediction. We conduct a random search on hyperparameters, and find that the best performing model has 8 LSTM layers of 275 hidden states and 88 FC hidden units. We think that this works best because a complex LSTM encoder encodes the most feature, and a simple decoder avoids overfitting. We then design a trajectory search algorithm that searches through all the candidates provided by the character classifier and produce a list of prediction words. We formulate this as a beam search problem. At each point, we only keep the top ranking sub-trajectories at this point. This is also a dynamic programming problem, where the optimal subtrajectory starting at each point must also be optimal for all subtrajectory arriving at this point when we combine them. We conduct a grid search through the 2 hyperparameters, number of split per letter, and also the number of beams to keep at each point. We find that a higher number of beams generally produces higher accuracy by giving more confidence options for the autocorrect model to work with, while a higher number of split can sometimes worsen performance by introducing unnecessary noise.
Autocorrection is our last step in the pipeline and is implemented based on SimSpell. We experiment with 4 different kernel methods to select the final prediction from top K candidates and achieve the high recognition accuracy of 88.8%.
However, we can see that the pipeline doesn't perform well with data that come from a new user. This is because the model is trained on a dataset from only 2 users. To solve this problem, we use a domain adaptation strategy to transfer the knowledge learned from the limited dataset to data collected from any user. We use the original LSTM model as the feature extractor and the letter classifier. Then we build a domain classifier that determines whether the input is from the new user. Finally, we use the adversarial training strategy that forces the feature embedding distribution to be indistinguishable among the users, but distinguishable among character labels. This strategy improved the new user data classification accuracy from around 13% to 17%. In conclusion, our handwriting word recognition system performed really well in our limited dataset, and we managed to leverage the feature learned in a small dataset to any user. We're looking forward to further optimize our algorithms and use them in various real-world applications. Thank you.